This is part two to the limits one notes. So we're going to start by talking about limits that do not exist. So limits that do not exist. We have three different types that we're going to pay attention to. So the first one is that the function approaches a different value from the left side of C than from the right side of C. So what this looks like is something like this. So if I have a graph, maybe from the left side, it's approaching some value that is up here. And then from the right side, it's approaching some value from over here. So that would be an example. The left side and the right side are not approaching the same value. Okay. The second one is the function increases or decreases without bound around C. So what that could look like, there's three different ways that this could look. So the first way could be something that goes like this. So as we're approaching 0, both sides are going up. It could be something like this. As we approach 0, both sides are going down. And then as we approach 0, one side could go up and one side could go down. Okay, so all three of these don't exist. More specifically, this one, as x approaches 0, would be going towards infinity. This one, more specifically, as x approaches 0, it would be going towards negative infinity. This one just doesn't exist. So all three don't exist, but this one and this one do have more specific answers depending on what's given as an answer choice. Okay, the last one is the function oscillates between two fixed values. So what this could look like as far as a graph goes is that it could just be oscillating, so bouncing and bouncing and bouncing and bouncing and bouncing forever and ever and ever. And it just keeps following that pattern over and over and over. So it's hard to tell what it's actually approaching. Okay, so the examples below, find each limit below if it exists. If it doesn't, tell why it's not a limit. So number one, the limit does not exist because the values are approaching. As we approach 0, the left and the right are approaching two different values, which would be option number 1. Okay, the next one, the limit as x approaches 0. This one also doesn't exist because it is increasing without bound or decreasing without bound. Or we could also say that the function is approaching a different value from the left and the right as it approaches C. So this could be a option number 2 or number 1. Okay. The next one, the limit as x approaches infinity of sine x. This does not exist because it is oscillating between two values. As we go towards infinity, it's always going to bounce between 1 and negative 1. So that would be option number 3. Okay, from a table, same concept. So as we look at this table, as we come from the left side, it looks like we're getting fairly small, going towards the negatives, potentially going towards, negative infinity. As we approach from the right side, okay, it looks like they're getting really big. So that could be going towards positive infinity. And so overall, the limit does not exist because the left side and the right side are approaching two different values, or it's increasing or decreasing without bound. But again, in the end, the limit as x approaches 2 of f of x does not exist. Okay, the next one, use the graph of the limit to the right to find the limit as x approaches negative 3 of f of x. So I just want to practice writing this out. The limit as x approaches negative 3 from the left side of f of x, that looks like it's approaching negative 2. The limit as x approaches negative 3 from the right side of f of x, looks like it's approaching 3. So that means that the overall limit, therefore, the limit as x approaches negative 3 of f of x does not exist. Okay, next part. So now we're moving into strategies for this. So now we're actually going to be doing this algebraically with some algebraic strategies. So first thing you always need to do is you need to try direct substitution. And then if that doesn't work, try to factor or cancel. Okay. So this first question is a previous AP test question. So here we go. The limit as theta approaches pi of theta secant pi, or theta secant theta. So automatically direct substitution. Once you plug in pi into the equation, you drop the limit statement. So pi secant pi. This is where we need to know that secant theta is the same thing as 1 over cosine theta. So cosine of pi is negative 1. So secant would be 1 over a negative 1, which is just negative 1. So we have secant of pi, which is negative 1. And we end up with a negative pi. And that is it. Don't rewrite the limit statement. Don't do nothing. Just it equals pi. Boom. Done. Okay. Next one, the limit as x approaches pi over 6 of cosine x. So again, direct substitution. We're going to plug in pi over 6. Cosine of pi over 6 is rad 3 over 2. And that's it. Okay. Next one, the limit as x approaches 1. So if we plug in 1 on top, we would get 1 plus 5 minus 6, which would be 0. Okay, and then when we plug in 1 on bottom, we also get 0. So what we would need to write is, write one thing first off, sorry. You never want to say that this is equal to 0 over 0. That is a no-no, and we will not write that. That will cause us to lose credit. Okay, so what we have to do when we get that is that we get the limit as x approaches 1 of the numerator, x squared plus 5x minus 6, that equals 0. And the limit as x approaches 0, of 1 of x minus 1 equals 0. Okay, so that's how you have to write it. You cannot write it as 0 over 0. That will count us to get lose credit. So now what we're going to do is we're going to try that factoring techniques. Okay, the factoring techniques say we need to factor the top. So the top, we need to think about what two numbers multiply to give us negative 6, add to give us a positive 5. That would be x plus 6 and x minus 1. The bottom is an x minus 1. Cancel, cancel. So that would leave us with the limit as x approaches 1 of x plus 6. Now I can plug in again. When I plug in, I get 7, and that's it. Okay, so a couple of things. Notice how, again, we don't write that. That's a no-no. We state that the top goes to 0. We state that the bottom goes to 0. Then when we factor, we still have our limit statement. When we simplify, we still have our limit statement, but once we plug in, the limit statement goes away. So that's super important. Okay, now the next one. Find the limit as x approaches negative 4 of r of x if r of x is a piecewise function. So this first part is when r of x does not equal 4. The second part is when r of x only equals negative 4. So this should say negative 4. Okay, so because this top one right here is when r of x does not equal negative 4, that is considered to be from the left side and from the right side. And the only time it equals negative 4 is at 1.7. Okay, so for the limit, we want to look at the left side and the right side, which means we're using that top equation. And so the limit of r of x as x approaches negative 4 would be 2 times negative 4 squared minus 3. That would be 2 times 16 minus 3, which is 32 minus 3, which is 29. And that would be the final answer. Okay, now how would this change if it said r of negative 4? Well, if it wanted r of negative 4, that's when you would use 1.7. Okay, evaluating it, you use that last one. For the limit, because of how it's written, you would use the left side and the right side. Okay, so you can try the check for understanding. That will be posted in the completed notes. Okay, and we're going to keep on moving through some examples. So we have a few more examples to get through. Okay, so number 5, the limit as x approaches 2. Oh, mine doesn't have a number, so hopefully yours has a number. The limit as x approaches 2 of that function. So again, if you try to do direct substitution, you would get 8 minus 8 on top, which is 0. Then you would get 4 minus 4 on bottom, which is 0. So again, as I said before, we do not want to write equals 0 over 0. That will cause us to lose all points, so don't do that. Instead, we're going to say that the top is equal to 0 and the bottom okay, so that right there is super duper important. That's something that's going to come up later on, and that is going to be something that gives us some points. Okay, so now what we need to do is we need to factor the top, we need to factor the bottom, and we need to see if there's something that cancels out. Okay, so when I factor the top, again, this step does require the limit statement. When I factor the top, they have an x squared in common, so I'm left with an x minus 2. When I factor the bottom, that's a difference in squares. I get x minus 2, x plus 2. So the x minus 2's cancel out. I'm left with the limit as x approaches 2 of x squared over x plus 2. I do direct substitution. I get 4 over 4, which equals 1. So again, pay attention to once we direct substitution, we drop the limit statement. But as we're simplifying, then we need to make sure that we're always writing this limit statement each and every time. Okay? Next one, direct substitution tells me that I'm going to do sine of pi over 6. So we did sine or cosine of pi over 6 earlier. Sine of pi over 6 is 1/2. Okay. Next one, again, always try direct substitution. When I do that, I get 1 plus 1 plus 2, which is 4. Then on bottom, I get 1 plus 1, which is 2. 4 divided by 2 is 2. So again, that's to show you, do direct substitution first. Next one, if we do direct substitution, we get 1 minus 1, which is 0, and 1 minus 1, which is 0 on bottom. So again, the limit as x approaches 1 of the top equals 0, and the limit as x approaches 0 of the bottom equals 0. Oh, sorry, as x approaches 1. Okay, so this does require some factoring. So what we need to know is about the sum and difference of cubes. This one is going to be a difference of cubes. So that would be a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. Okay, so that's the formula right there. And so that's how I'm going to factor this. So we have the limit as x approaches 1 of x minus 1 times x squared plus x plus 1 all over x minus 1. I see that these cancel out. And so if you wanted to, you could go ahead and do direct substitution. 1 squared is 1 plus 1 plus 1, that is 3. You do not actually have to write that next step of it simplified out. Boom, like that, and you could be done. If you wanted to, you could have wrote one more step and gotten the same thing. So it kind of depends on you on when you are ready to plug in and not plug in. Okay, so either way it works like that. The next one. This one is going to require a double angle identity. So the double angle for sine of 2x is equal to 2 cosine x sine x. Okay, that is something that we learned in pre-calc right there. And so, again, if I tried direct substitution, sine of 0 is 0, sine of 2 times 0, which is sine of 0, is 0. So again, the limit as x approaches 0 of sine x equals 0, and the limit as x approaches 0 of sine 2x equals 0, making sure that we don't do that 0 over 0 notation because that's improper. And so now we can use that double angle identity that I talked about before. So on bottom, it would turn into 2 cosine x sine x. I see that I have a sine x on top, a sine x on bottom, and so that leaves me with the following. The limit as x approaches 0 of 1 over 2 cosine x. That would be 1 over 2 cosine of 0 is 1. So I get 1 over 2. Okay, this next one is a little bit more involved. Again, direct substitution, I'd get 0 over 0. So the limit as x approaches 0 of the square root of x plus 1 minus 1 equals 0. And the limit as x approaches 0 of x equals 0. Okay, so what we're actually going to do before we write our limit statement is we're going to do the algebra behind. Okay, so how we're going to do this is we're going to take this part right here that's inside the limit statement. We're going to do our math. Okay, and we're going to multiply by the conjugate, which is the square root of x plus 1 plus 1. And if you multiply the top by something, you do have to multiply the bottom by something. So we're going to multiply this out. The square root times the square root cancel out and just leaves you with an x plus 1. The square root times 1 gives you a positive square root of x plus 1. This negative 1 times the square root gives you a negative square root of x plus 1. And negative 1 times 1 gives you a positive 1. Okay. On bottom, you never have to multiply out the bottom. You never have to multiply out the bottom. Now, eventually you'll see the pattern, but every time we do this, these middle two terms are going to cancel out because we're multiplying by the conjugate. So you don't have to worry about doing all of that. And so now we see that we can go ahead and go back to our limit statement. And we can write out x plus 1 minus 1 over x times the square root of x plus 1 plus 1. Okay, we see that the 1's cancel out. And then I see, let's rewrite and see what we have. The limit as x approaches 0 of x over x times the square root of x plus 1 plus 1. I see that now this x cancels out that x, and so I'm left with a 1 on top, and I can go ahead and direct substitute. When I plug in 0, I get 0 plus 1, which is 1. Square root of 1 is 1, plus 1 is 2, and so we get that right there. So that one is a little bit more tough and challenging. And then something that would just be safe to do is if you just draw an X through this right here, the reader won't grade that work. So just in case it's something that maybe we messed up in, we're not going to be counted off for it. Okay, so that is the limits. Doing the additional practice is really going to be helpful. Go ahead and try the check for understanding. That is posted in the completed notes so you can check yourself. If you have any questions, please make sure you write them down and ask for help.